Well, welcome back to part 2 of getting started with Easy5 for Adams users. If you haven't watched the first video, I would encourage you to do that. In that video, we just introduced the problem of this simple mass spring damper system, and we showed various approaches to solving the dynamic response of the system in Easy5 using the block diagram approach, using the transfer function approach, using the Easy5 mass spring damper component, and then using live co-simulation with Adams. What we're going to do now is we're going to look at including nonlinear physics into our model, friction and bump stops, and then adding a PID controller. And so really what we had in the first model was the very simple system without friction or bump stops. We're now going to include friction, which is a highly nonlinear physical phenomenon, particularly in terms of it being discontinuous between static and dynamic friction. As well as the highly nonlinear behavior of a system that includes 3D contact, where the mass will make contact with the bump stops. And so we're going to look at various ways to do that. And so let's start by going into Easy5, and or let's start by going to Adams, and we're going to activate friction in our model. So we're going to activate friction and tell Adams to now include friction in the model. And this is part of the joint functionality. If you right click on any joint in Adams and you go to modify, you've got this option down here to include joint friction. And so there you can see the friction properties of this joint, and you can see that we've given it a static friction coefficient of 0.002 and a dynamic friction coefficient of 0.001. They are both low values because I didn't want friction to heavily dominate the system, but I wanted it to be clearly visible. And we're telling Adams that we want to include both stiction and sliding. And I'll show you a little bit more about that in a minute. So we've now added friction to the model. We've activated the friction component. Before we can run this model from Easy5, we just have to re-export the plant. And so we just go to an existing control plant. We pick the one that we did previously. It loads all the values, and we simply say OK. So all this does now is it writes out the new Adams solver file in the background, which now includes friction. And so anytime you change something in your Adams model, just remember that you must go to your plant export and re-export the plant. Otherwise, that information won't be included when you run the Easy5 model. So we're going to now move over to back to Easy5 and see if we can introduce the same friction into our single mass component. And so we simply double click on that, and here you see we've got a dynamic Coulomb friction force and a breakaway friction force, which is effectively the static friction force. Now, the difference between Easy5 and Adams is that Easy5 is expecting the friction as a resultant force in newtons. And so we have to do a little bit of maths here. We're going to simply say equals the friction coefficient 0.001 times the mass of the block times gravity. So the normal force times the friction coefficient gives us a dynamic friction value of 0.4905 newtons, and the static friction is simply the static friction coefficient times the mass of the block times gravity, and we should get a value that's twice the size. Okay, so we now have the stiction force and the dynamic friction force. You will know if you've looked at the friction modeling in Adams that Adams hates numerical discontinuities, and so Adams applies a kind of a smoothing algorithm to transition from static to dynamic friction. Easy5 is much better at handling numerical discontinuities than Adams, and so it has an option for an exact formulation which uses something in Easy5 called switch states, which really allows the solver to switch from one value to another. But you also have the option of a smooth approximation. And if you click smooth approximation, you'll see here in the documentation that it explains it very similarly to Adams, that you then have a smooth step function that transitions from your static friction to your dynamic friction. But we're going to use exact formulation because that's exact and we want the right answers as far as possible. Okay, so we've added friction to this block, we've added friction to our Adams block, and so we can run the simulation. So let's do that. And so Easy5 needs to compile a new executable, which it's doing. It compiles, builds, and then starts the simulation. So there we have Adams firing up in the background. And we should be able to see the difference now. So they all start off together. But what we're seeing here now in MassDX, so that's the Adams model, and the red one is the Easy5 component with friction. So you can see the two graphs differ from the original two linear mathematical formulas that don't include friction. And what's particularly interesting here is we're going to see that the two models with friction will actually reach steady state much sooner, as would be expected, because friction introduces another degree of damping to the system. And so you'll see that about now we're going to actually start settling into a steady state, whereas the blue and the yellow graph continue. All right, so there we can see the Adams model and the Easy5 component with friction have now reached steady state. They've settled, whereas the models without friction continue to oscillate for much longer. So let's stop that. And we'll bring up the post processor and be able to look at the comparison of the results. Right, so very interestingly up front, we see, for example, in various graphs, a bunch of discontinuities which were not there previously. And this is obviously because of the frictional force changing from dynamic to static with discontinuity. So let's load our previous graph, which compares all the results. And we want to now add the Adams results. So we add a new curve, and we bring in the Adams, that's mass dx, all right, and it's sky blue, that's fine, let's make it 2. All right, so we can zoom in up here, and what we will see is that the original two models are the same. What we see is that the Adams and the Easy5 model with friction are, again, in terms of peak values, almost identical. Slight discrepancies in terms of a bit of a phase shift or a lag. But what we'll see here is quite interesting, and that is that the Easy5 model changes from its dynamic motion to its static instantaneously because we told it to use the exact formulation, whereas the Adams model transitions gradually from movement to settling, from dynamic friction to static friction. And so there's a slight discrepancy in the final answer. And this you would expect. And so in this case, the Easy5 model is correct. It's the exact numerical formulation of friction from static to dynamic, whereas the Adams is an approximated approach. And what this allows you to do now is to go back to your Adams model and actually play around with some of those parameters in the friction box, in the friction dialog box, until you get an acceptable answer. And so if your model is highly susceptible to friction or the transition from static to dynamic friction, that's kind of one of the unknowns in Adams. You know, have I got it modeled accurately enough for my purposes? Well, by using the Easy5 block, you actually get the exact mathematical answer that is correct, and you can try and tweak your Adams model to approximate an answer that is good enough for your purposes in that way. All right, so there we've introduced friction to both models, and we can see that they're behaving well. What about bump stops? And so let's just do that quickly. We're going to open up our Easy5 model, and we're going to put in a bump stop at 25 centimeters and minus 25 centimeters. So the mass can't move more than that. And then we're going to go across to our Adams model, and and activate these contacts. So I've got two 3D contacts, which we're going to now activate so that we include the contact in the model. So we activate that. So now both 3D contacts are activated with these blocks. And remember, because we've changed the Adams model, we have to just re-export the plant. So we simply say, OK, writes out a new Adams model, and we are now ready to go back to Easy5 and to run. But the problem is the force we're using is not pushing the block far enough to hit the bump stop. So let's just go to our step function here, and under inputs, we're going to make the input force, let's say 35 newtons. That way, when the 35 Newton force on the block, it's going to hit the bump stop. Remember, our top two approaches, the standard equations of motion and the transfer functions, they know nothing about bump stops or limits, so they're going to allow a lot more movement than the Easy5 component or the Adams model will allow. And so we should now notice quite a big difference between the top two results and the bottom two results. So Adams is just firing up in the background. Okay, bring it across. And let's have a look. All right, so initially, okay, there we bump. All right, so the original two models allow up to almost 40 centimeters of movement, but the Adams model and the Easy5 model have now prevented movement beyond 25 centimeters. And so because of that, you see the model settles much more quickly. And so the behavior now is completely different from the original approach now that we've introduced the bump stops. All right, that's far enough. Let's stop the runs and let's just go and scrutinize the results a little bit so that I can show you something quite interesting in terms of the way Adams models contact versus the way Easy5 models the bump stop. So we bring up the plotter and just reload our layout file. We bring up our graph here, and these points have now changed. Now, what's very interesting is, again, you see the difference over here around the friction. So the Adams model settles at a slightly different steady state value because of its smooth approach to friction. But what's very interesting is if we zoom in here, what you will see is that the Easy5 model, because it can handle perfect numeric discontinuities, when it gets to 25, it immediately stops the movement. Adams, you will know, using an impact statement to model 3D contact, requires a certain amount of penetration between the two bodies in order to generate the contact normal force. And so here you can see that the Adams solver actually overshoots the 25 centimeter limit in order to generate the reaction force necessary to push the block back to the 25 centimeter mark, and then the two follow again exactly the same. And so this just shows you that in an Adams model, you can play around with the stiffness and the damping and the penetration, the penetration factor that's allowed in terms of triggering contact in Adams. The more you try and approximate this, the more the Adams solver is going to battle because you are approaching a numerical discontinuity. But again, here you can see that once the contact event has taken place, Adams and Easy5 almost behave exactly the same. All right, so there we've been able to add two sources of nonlinear physics to the model, friction and bump stops. And the last part to this video is now to add a control system which will allow us to move the block to exactly the desired location by adding a PID controller, and that we'll do in the final part of this video.